Hello again. This is Math 2232 coming to you from the College Edu page, and the title of this lecture is Convergent Tests Summary and Application Guidance. As always, please be an attentive learner while watching this video. By way of introduction, now that we've covered a whole bunch of the tests, it's time to think about organizing them into a general set of guidelines to help us determine the convergence of a series. Note that what will follow are a general set of guidelines, and because some of these series can have more than one test applied to them, we'll get a different result depending on the path that we take through the set of guidelines. In fact, because more than one test may apply, you should always go through the list quickly and identify all the possible tests that can be used. Once you've done this, then you can identify the test that you feel will be the easiest for you to use for the particular situation. With that said, here's a set of guidelines for determining the convergence of a series, and there is no substitute for practice. Number one, with a quick glance, does it look like the terms of the series don't converge to zero in the limit, i.e., does the limit as n goes to infinity a sub n not equal 0? If so, the divergence test is a good one to use. Note that you should only do the divergence test if a quick glance suggests that the series terms may not converge to 0 in the limit. But remember, if they don't converge to 0, then you know it diverges. Number two, is a series a p-series? That's the summation of 1 over n to the p, or a geometric series, summation n equals 0 a to the Rn, or the summation from n equal 1 to infinity a to the Rn minus 1. If so, use the fact that the p-series will only converge if p is greater than 1, and a geometric series will only converge if r is less than 1. The absolute value of r is less than 1. Remember as well that often some algebraic manipulation is required to get a geometric series into the correct form. Is the series similar to a p-series or a geometric series? If so, you can try the comparison test. Number four, if the series is a rational expression involving only polynomials or polynomials under the radicals, i.e., a fraction involving only polynomials or polynomials under radicals. If so, try the comparison test and or the limit comparison test. Remember, however, that in order to use the comparison test and the limit comparison test, the series terms need all to be positive. Don't forget that some series can be telescoping series. In this case, they can be summed, and the only way to test this is to do partial fractions. Also, if it's a geometric series, again, perhaps with some algebraic manipulations, it can be summed exactly. Number five, does a series contain factorials, or constants raised to powers involving n? If so, then the ratio test may work. Note that if the series terms contain a factorial, then the only test that we've got that will work is the ratio test. Can the series terms be written in the form an equal minus 1 to the n bn, or an equal minus 1 to the n plus 1 bn? If so, then the alternating series test may work. Remember, you have conditions that you must verify in order to apply this. Number seven, can the series terms be written in the form an is equal to bn to the n? If so, then the root test may work. And if an is equal to f of n for some positive decreasing function f, and the integral from a to infinity f of x dx is easy to evaluate, then the integral test may work. And again, remember that these are only a set of guidelines and not a hard and fast rules to use when trying to determine the best test to use. There is no substitute for practice. If more than one test can be used, try to use the test will be the easiest for you to use, and remember that what is easier for someone else may not be easy for you. So that's why practice pays off again. Also, just so we can put all the tests into one place, here's a quick listing of all the tests we've covered so far. The divergence test. If the limit as n goes to infinity of a sub n does not equal to 0, then the summation a sub n will diverge. The integral test. Suppose that f of x is a positive decreasing function on the interval from k to infinity, and that f of n is equal to a sub n. Then, if this if this integral from k to infinity f of x dx is convergent, then so is the sum from n equal k to infinity of a sub n. If this improper integral from k to infinity f of x dx is divergent, then so is the summation from n equal k to infinity of a sub n. They converge and diverge together, but not to the same value. The comparisons test states, suppose we have two series, summation an and summation of bn, and they both are positive terms, non-negative terms for all n, and an is less than or equal to bn for all n, or more generally in the tail. Then, if the summation of bn is convergent, then so is the summation of an. If the summation an is divergent, then so is the summation of bn. We also studied a more sophisticated version of a comparison test called the limit comparison test. Again, suppose we have two series, summation of an and summation of bn, with an and bn bigger than or equal to 0 for all n. Define c to be the limit as n goes to infinity of an over bn. If c is positive and finite, that is bigger than 0 and less than infinity, then either both series converge or both series diverge. That is, they converge or diverge together. So you pick a test series that you know about the convergence and apply this test. It could either converge or diverge because these will converge or diverge together. We also studied the alternating series test. Suppose we have a series, summation of a sub n, and a sub n is either equal to minus 1 to the n bn or equal to minus 1 to the n plus 1 bn, where all the bn's are greater than or equal to 0. If the limit as n goes to infinity of b sub n is equal to 0 and bn is eventually a decreasing sequence, then the summation an is convergent. Here are the ratio test and the root test. The ratio test. Suppose we have the series summation a sub n, and we define L to be equal to the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Then, if L is less than 1, the series is absolutely convergent, and hence convergent. If L is larger than 1, the series is divergent, and if L equal 1, the test fails. That means the series may be divergent, conditionally convergent, or absolutely convergent. We have the root test. Suppose that we have the series summation a sub n. Define L this time to be the limit as n goes to infinity of the nth root of the absolute value of a sub n, which could be written this way: the absolute value of a sub n raised to the 1 over n. Again, the conclusions are similar, but about a different L. If L is less than 1, the series is absolutely convergent and hence convergent. If L is greater than 1, the series is divergent. If L equals 1, the test fails, and the series may be divergent, conditionally convergent, or absolutely convergent. And Mike McCabe often talks about making note cards. Here's one possible organization where we have that information all contained here, and it even includes in these notes talking about the telescoping series, and the geometric series. So you can define what is the test called to use the right vocabulary. You can have notes about how to recognize the series. What does it look like? What are the conditions of convergence? For example, for the geometric series, we have, it looks like the summation from n equals 0 to infinity of a times r sub n. It converges if the absolute value of r is less than 1. If the absolute value of r is greater than or equal to 1, it will diverge. And here's comments. In fact, this infinite sum exists, and it's the first term divided by 1 minus r if the absolute value of r is less than 1. So creating a summary sheet that looks like this could be very useful for you as you prepare for examinations. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We are all in this together. May God bless you all.